So today we start with to discuss the matrix representation of the operators in quantum mechanics. We have introduced the operators and their general properties, their multiplication rules, and also the correspondence in the dual space and the Hermitian operators and the eigenvalue problem of the Hermitian operators, etc. So essentially we have more or less a proper understanding on the entities which live in the vector space which we associate with the quantum mechanics. There are vectors which we associate with the physical states, and there are operators, particularly Hermitian operators, that we associate with the dynamical variables. So let's proceed further on a nice subject, which is the matrix representations of the operators. In a sense, in this way, we are going to find some relationship between the operators and the very basic states which we call the eigenvectors of these operators. Anyway, let's proceed and let's see how we get that representation rather quickly. As we have indicated, mostly we are going to deal with the Hermitian operators as they have the real eigenvalues so that we can establish contact with the physical reality in the laboratory. But here, let's keep the discussion as general as possible. Let's consider arbitrary. An arbitrary operator. Well, X is reserved for as a notation for the arbitrary operators, and A, capital A, for the Hermitian operators. But anyway, this is independent of the Hermitian nature. So here is a nice trick. We have seen that eigenvectors of the Hermitian operators have certain nice properties. That is, those eigenvectors corresponding to different eigenvalues are orthogonal to each other. As we normalize to make them physically meaningful, they are orthonormal. So as a general rule. And then they are complete. And the completeness of the property was based on the fact that any general state in that vector space can be expanded in terms of a basis set. And so that assumption, in a sense, or postulates, according to certain people, gives you a plausibility argument that these eigenvectors should be complete. And we have come up with a nice mathematical expression to express for the completeness, which I'm going to use in a moment. So let's put this operator in and here insert identities. That's a nice trick. When you say identities, what is a natural representation of an identity? That is the completeness relationship of any particular basis. And the natural bases, as I have mentioned, are offered by the eigenvectors of the Hermitian operators. Let's denote that Hermitian operator by a capital A and their eigenvectors accordingly, as we have seen before by this notation. And that's indeed an identity because that's the completeness relationship of the eigenvectors. And that was as particularly the last subject that we have discussed last time. And also let's introduce again the similar identity in here. You can multiply this operator from left and from right by identities, right? Without changing anything, and that's what I'm doing. Multiplying it from left by an identity and multiplying from it right by an identity, which is, again, the completeness relationship. Notice that I'm using different indices for obvious reasons, because we don't want to keep the discussion as general as possible. Okay. We want to keep the discussion as general as possible. Sorry for the bad language. So let me rearrange this and write it as I and J. Here there is an AI, and here is AI, X, and AJ, and then AJ. You see, I haven't really done much. What I have done was insert identities from left and right. Then I have identified a central object in here. Notice that it is the matrix element of the X operator between AI and NJ, two different eigenvalues, eigenvectors of the Hermitian operator. So put aside as a side remark, what are those things that I'm using? Okay. I use a Hermitian operator, their eigenvalue equation is eigenvalue equation written as such, eigenvectors and eigenvalues. Notice that without really specifying explicitly, I'm assuming that it is a non-degenerate problem. And how do we accommodate degeneracy eventually? I will talk about it a little later today. So there is no problem. There is one eigenvalue and one eigenvector. So it is, there is a simple way of counting it. So there is no mismatch at this level between the dimensionality of the vector space that we are considering and the number of independent eigenvalues. They are the same. There are as many eigenvectors and eigenvalues because we have non-degenerate regime, and therefore dimensionality is that particular number, the number of the eigenvalues. So notice here that this is really the central object could be thought as a matrix representation of this operator. You see, I have to use this careful language. So I identify it as a matrix representation in that basis AI. And you may, those of you who are experienced a little bit in the linear algebra, you may say, why matrix? Well, you'll see in a moment that it is in conformity with the matrix multiplication rule. Matrices are tables, right? Not always square, but in special cases, square tables. And like if it is n-dimensional, n times n square table, there are entities sitting in each position. And in order to really call it a matrix, when you try to combine these two tables to form another table of the same nature, n by n, there must be a certain multiplication rule obeyed. So that's the important thing. When I say matrix, I will demonstrate that it obeys the matrix multiplication rule. Okay. So let's proceed a little bit. For instance, how do I define the Hermitian adjoint in this matrix representation form? Remember, in our original definition of the Hermitian adjoint, we have used the following. We said X acting on an arbitrary ket vector, and the dual correspondence from this ket space to so-called bra space, together which we were able to define an inner product. Well, that was the definition of the so-called Hermitian adjoint. Okay, and we have obtained, last time, again, let me just, instead of going through the derivation, we have obtained the following expression. So this was the relationship between X dagger and you, of course, rightly looking with warning eyes that I should have a complex conjugation in here. So this is alpha and beta are arbitrary kets in that space. And when you take this expectation value of the operator, that is how they are related to each other. Well, this is sort of a correspondence type of not a very, how do you say, operational definition. It is symbolic. And this is more operational a definition, right? You attribute a certain meaning to X dagger by saying that X expectation value, well, or its matrix elements between two different cats are related to the original X's matrix elements in that manner. Now, let's convert this relationship to the new language. So if I have, if I use this expression for the eigenvector of the eigenvector, in the eigenvector basis of the operator that I have been talking about, what do I get? I get the following: AI x aj is aj x dagger AI complex conjugate. Well, actually, instead of this, I better write it in the following fashion. Let me take the conjugation of the equation, complex conjugation, once more. Complex conjugation of the conjugation is the same. It takes you back, right? You take complex conjugation once and then another time you go back. So in a sense, this is more telling. It is the following: the matrix element, or the matrix representation, now I can use that language safely, of the Hermitian adjoint operator is obtained by taking the transpose and complex conjugate of the original operator. Well, this is, in a sense, for all of you, a more familiar definition of the Hermitian adjoint, right? So you take the complex conjugate and transpose together of the matrix element of an operator, and you get the matrix elements of the corresponding Hermitian adjoint operator. Okay. Okay, let me now proceed with the, well, this was the matrix representation of a matrix representation of an operator, sorry. And now let me proceed by considering the following equation. That is, when you act on a state vector arbitrarily chosen in the space alpha by the operator x, again arbitrarily chosen from that space, you get another cat, right? That's usually the rule. Well, that's the meaning of a vector space. It's closed. It contains all these entities together. It is closed under these multiplications. So what about the matrix representation of this equation? In order to consider the matrix representation, what I have to do is project this on, say, AI, both sides. So let's see, what do we get? AI beta AI x alpha. Well, I have to use the previous discussion concerning the matrix representation of operators in order to see that entering in here. Obviously, I have left some blank in here. Let me introduce here an identity. As always, identity is the completeness relation of the eigenvectors of the operator A. So what do I get in the right-hand side? I get J AI X AJ AJ and alpha. So I'm in a better position to interpret what the new entities which I need to interpret are those entities. Because this was already defined to be the matrix representation of the operator x. So what do I call those? Remember, I started with the arbitrary alpha and beta cats in the cat space, and I have projected them on the basis vectors, along the basis vectors of the operator A, arbitrarily chosen again. So as this is, then you remember that this is a matrix representation. So it's a square matrix n cross n. So what should be the representation of the betas in that basis? Because essentially the projection of it gives you a representation. You may have two things coming to your mind. It could be either a column matrix, a row matrix. So what if it is a column matrix? When you have a column matrix multiplied from left using the matrix multiplication rule, by a square matrix you get a column, and the left-hand side was identified together as a column. So this is a consistent identification, obviously. You may say, indeed, what we are doing is correct. Well, although it's more or less trivial, we have the answer, so there is no need for further elaboration. But what if I have chosen this? I have chosen to represent this as a row matrix. Now notice that if I am using, as this is a matrix, and in handling matrices, I have to obey the matrix multiplication rule. So if I have to use the matrix multiplication rule, then if I put a row in here, together with this, of course that doesn't obey the matrix multiplication rule, right? Because when you multiply a row from left by a square, it is an illegal product. It doesn't give you anything. So that option is out. And this thing should be represented by a column matrix. And indeed, it obeys the matrix multiplication rule. Because this thing is labeled by an index j. The second index of it is a j. Therefore, j's are contracted. The free index is I, carried by the free index in here. That is the label of the row, the columns, rows of the column. You may think it's trivial. It's an unnecessarily trivial discussion. It's not really, because there is a nice mathematics. In here, you have to use a careful language, obviously. Fine. So, yeah.
You said multiply the matrix from the right side is forbidden.
No, that's not what I said. I said if you are using, if you call this a matrix, that was the starting point. Obviously, all these tables, square tables, when they are combined or multiplied in the mathematical language, if they are called matrices, they should obey the matrix multiplication rule. What is the matrix multiplication rule, by the way? If you have two matrices, this is now ordinary matrix that I'm talking about from mathematics. So you have these two matrices. How do you multiply them? Symbolically, you say this is the ij, so it is aik sum over k, b, kj. The rule is that their neighboring indices are the ones which are to be contracted. That's the matrix multiplication rule. Here I am saying that if I choose to represent this entity with a column matrix, a column matrix would be just having an index like this, right? It's only natural that I can use it like that. Sorry, J, because that's a J. If I choose to denote this as J, and this is the ij, and J's are contracted properly, so it's a matrix multiplication rule. But if still represented alpha j and use a row, then you cannot really contract this. It's an illegal product. That's why I say it must be represented by a column matrix. Okay. So what is the representation really? Let me fill in this representation. Instead of using a special new space, this is nothing but the A1 beta, A2 beta, a expression of that form. When eventually, in a few minutes, when I pick up the spin 1/2 problem for illustrative purposes, you'll see obviously how it goes, because when it's sort of an abstract notation, it may sound a bit closed. But anyway, so let me proceed with the corresponding equation in the dual space. What is the corresponding equation in the dual space? We may have an expression of this sort. Well, another operator, say, call it y if you want. But in order not to change notation, I write x. I'm not taking the dual correspondent of the original. If I do, I should have taken x dagger. That's the reason why I add that additional qualification. A different operator written in that fashion. You act on the bra. This time you have to act on from the right, that was already seen before, to get another bra. So what is the matrix representation of this bra type of relations in the dual space? Again, you project this on the basis vectors of a specially chosen Hermitian operator. And what do you get in the left? What you get in the left is this, alpha x ai. Again, as before, and insert here, just to that position, a identity, which is nothing but the completeness relation of the Hermitian operator. And then you get the desired relationship. Beta ai is, ai, j alpha aj x ai. Okay. Question. Well, as there's no problem with this entity, whether it was obtained in the ket relationship or bra relationship, we have already identified it as a square matrix. There's no question about that. The next question is, in relation with this one, how do we represent this one? This was a column matrix. The ket projected along a basis vector. Now here, the bra projected along a basis vector. Matrices are to obey matrix multiplication rule. Therefore, if I bluntly attempt to identify this with a column matrix, I'm not writing it because I don't want to leave any traces, it's wrong. Okay, if I continue doing it with a column matrix, so a column in the left multiplying a square in the right, that's an illegal product. It doesn't obey the matrix multiplication rule. Obviously, in order to obey the matrix multiplication rule, I have to represent this. Use a different color, yes. With a row and a square. A row from the left acting on the square from left gives you a row, so a row is equal to a row. So it's a legal description. Lesson. The projection of the kets along the basis vectors are represented by column matrices, and the representation of the bras along the basis vectors are to be represented by row matrices. You may say, are there any relationship between row elements and the matrix and the column elements? Yes, there is indeed a relationship. If you're not using the symbolic matrix language, but using C-number language, of course, this particular identification may be of more relevance. So let me write that. We know the definition of the properties of the inner product, remember. We have listed as two axioms. And from that, obviously, we see the following. AI alpha is a ket. I can write it as alpha AI complex conjugate. Therefore, you know that those row elements associated with the bra relationship are really complex conjugate of those things which enter into the column. Okay, column matrix representations. Fine. Okay, that is the bras and cats, the matrices associated with the bras and cats. I use careful language. I'm not saying that they are matrices. They are represented, or they correspond to those matrices when you go to the matrix language, okay? Because you can use any representation or any language you like. Using a representation is one language. You can directly work with the operators. That's another language. They are all perfectly all right. Now here it comes the following. A next quantity which may require to be represented by matrices again is a very particular operator that we have construct. Let me use the notation I used in the notes. So let me consider such an outer product. Well, when you take the inner product of two cats, you get a complex number as, you know, alpha, beta, right? Okay, let me compare this against, alpha, beta. This was the inner product of two cats. Remember, this is the language we use. It is the inner product of two cats, but you get the one cat and the other one in the dual space, and that's how you come up with a complex number. Okay, inner, that's the definition of inner product. And this is the outer product of two cats. The outer products are defined by taking that cat and its bra, but you put the bra first. Well, the details of it was discussed. And we have shown that it indeed acts like an operator in detail. So if it is an operator now, this is a complex number, C number. This is an operator, right? Okay, it's good always to remember. So how do I represent this outer product of two cats in the given basis AI, for instance? And we do it in the following manner. Okay. We take the matrix element here. If you want, that's a funny language, I know, but I do it on purpose. I exaggerate a little bit, right? How do you get the matrix element? If it is an operator, you sandwich it between AI and AJ. If so, then what do you get? AI, beta, and alpha, AJ. Question. Is this a matrix indeed? If I call it, say, Xij, for instance, is this a matrix? It's indeed a matrix, right? And what are the matrix now representation? It is the following quantity. If you call this, let me give them names. This is beta I, for instance. This is alpha j star, because go around it and we define the cat from the right and the projected vector in the left. So it has an expression of this form. So what is the matrix representation? It's not equal, it corresponds to, it's a representation. So beta 1, alpha 1 star, beta 1, alpha 2 star, beta 2, alpha 1 star, beta 2, alpha 2 star, etc. So that's really the matrix representation you get for this beta alpha entity, which is obtained by taking the outer product. But whereas this is just a pure innocent number, right? This one. How do we represent that this is an innocent pure number? You insert an identity in here, AI and AI, sum over I, of course, is understood. A sum is I, and this is alpha I star beta I. A single sum, right? Notice that this one is a single sum. Whereas this one is a matrix. Okay. By the way, now let's carry this over. We are proceeding nicely. Notice that once you get used to the notation, it is not that cumbersome really. All you have to do is use the usual language of mathematics associated with these vector space. So it's linear algebra really what we are doing. Okay. Now if I have now a Hermitian operator A, and if I use its eigenvectors to get the matrix representation, what do I get? So matrix representation in its own eigenvector basis. It has been a little too long, but really I need to write it as long as that. Here is the A I'm talking about, the operator and its eigenvalue equation is defined in this manner. So I am trying to find the matrix representation of this in its own basis. Well, there are several ways that I can proceed. One is just to go to AJ, or I will do something a little slightly different. Do it on your own. Just project this on AJ, and you'll get the matrix representation. It's going to be diagonal. Let me do it. It's a trivial thing, but I will do something better. So let me do the quick one first. I project this on AJ. AI, the right-hand side, this is the number, AJ, AI, using the orthonormalization property, orthonormality of the eigenvectors of the Hermitian operator. So tacitly, I am assuming that it's a Hermitian operator. A is reserved for the observables, which are Hermitian operators. X is reserved for general operators. So whenever I don't even specify it explicitly, think of that I'm using the Hermitian operator. So otherwise I wouldn't be able to write this, right? The orthonormality property. So what do I have? Here is the matrix elements between I and J. Here is the real eigenvalues of that. And there is a delta ij, showing that what is the matrix form then? This right-hand side is A1, A2, A3. Obviously, that represents a diagonal matrix. Natural. More or less something that you are familiar from your past experience. So next thing I will do is a slightly more general form of that equation. Let me write now A operator and insert an identity from left I and insert another identity from right. By now I'm sure you have gotten used to this insertion of identity using this beautiful trick of completeness relation. It's so operational. So what you have then, sum over I and J, AI, AI, A, AJ, AJ, right? Nothing new, we have seen this before. Here I can use this expression that when it acts on it gives you the AJ, and they use the orthonormality. So it is AJ delta IJ. And then carry out one of the summations, taking advantage of delta. it becomes I, AI, AI, AI. A funny relationship, but a beautiful relationship, really. It's a joke that I call it funny. It's so powerful. You'll see that when I go to the spin 1/2 problem, it's going to give off so much information. It's a trivial thing, but sometimes slips from your mind to use these beautiful, simple relations. So I'm enjoying, as you see myself, that to influence you that you should really enjoy using these tricks. So what is this? AI, AI, AI. This is the operators. So this gives you a beautiful way of representing an operator in terms of its projectors. The projection operators associated with these eigenvectors. So there are projectors in the game, right? Each these A1, A1, A2, A2, A3, A3, all the way covering all the spectrum. They are the projectors. They project along those entities. So we denoted this lambda I. Therefore, this is now I, AI, lambda I. So when you have any operator, you can really represent it in terms of, if you know the eigenvalues, if you have an operator, in principle, you know the eigenvalues. So if you know the spectrum, that is eigenvectors, you can form the eigenvectors, you can form the projectors out of the eigenvectors, and you represent the operator itself directly in terms of the projectors. That's a very powerful theorem. Okay. Notice that I'm using a slightly different language than the textbook I have suggested. He uses primes, single prime, double prime, triple prime. That's cumbersome. I use I, J, K. So it is easy to label the things. Otherwise, there is not much difference. Okay, let's illustrate this. As I said, it's such a powerful theorem. It really pays that the illustration. Let's consider the famous spin 1/2 problem that we had accumulated some experience before in the context of Stengerla experiments. And we have seen that there are, we usually take as the default direction of the magnetic field in the Stengerla as the z direction. Therefore, we have the z component of the spin operator, which enabled us to define everything. So we had its eigenstates, that the state of the spin along the magnetic field, if it is parallel, we call it the plus up state, and if it is anti-parallel, we call the state of that spin as the minus. Usually we put these z's, but if we drop those labels, we should understand that it's a default state, so it should be what? Then it should be the z ones. If there are no labels, it is the z direction. But when it comes to x and y directions, we have to put the labels in because it's not our default direction. That's a convention element. If so, and what are the associated eigenvalues when the spin is up? We have really analyzed this using the experiment. It is h power over 2 and minus h power over 2. These are the associated eigenvalues for this up state and down state along the z direction. Can we really mimic all those general abstract discussions on this specific problem? Yeah, the first thing is, remember, there was something which we have discussed last time associated with this. We have seen that the lambda i's were equal. This is the completeness relationship, right? When you sum all the projectors, you add them, you get 1. When you multiply the projectors with the associated eigenvalue and add them all, you get the operator itself. And there are further higher forms of this, but I'm not going to get into that. Eventually, you may wish to study them on your own. If so, That's the first relation and that's the second relation. What is the first relation associated with this? There are two projectors, right? The first projector is this, the projector along the up direction, and the projector along the down direction. So in our notation, that's lambda plus, and that's lambda minus. That gives you the 1. There are two alternatives, either up or down. So the up and down together forms a complete set. That's the completeness. And that's the expression of the completeness relationship. Second, I should get the SC. Again, this expression comes to rescue us. It is h bar over 2, the plus projector, plus minus h bar over 2 times the minus projector, right? That's, if you want, lambda plus lambda minus is sum is equal to 1, and the associated eigenvalue times lambda plus associated eigenvalue times lambda minus is the SD itself. So what is it? H bar over 2 plus minus, because this minus, minus. How nice, indeed. By the way, let's talk about the matrix representation. I have employed the previous theorems to get these two beautiful expressions in terms of the projectors. And what about the matrix representation? You say, in what basis? Let's take this is the basis of the matrix representation. In the basis. As I said, you may think that it's unnecessarily detailed language, but it's not. When you are talking about the matrix representation, you have to specify the basis, obviously, right? Without any question. So, what are the representation of the pluses themselves? If you are talking about the matrix representation, you have to talk about the matrix representation of the basis vectors themselves. Everything should be consistent. So what is the matrix representation of this? That is following us. I have erased that, following the column thing. So it should be plus, plus, and minus, plus, correct? This is the ket that enters in here, and you project them along the bases, plus and minus. Plus, plus. They are normalized, right? Because that's what we call them basis vectors. By the way, perhaps I should express in here that plus plus is 1, and minus minus is 1, plus minus minus plus is 0. That's the definition of a basis vector. So it's already at the back of our mind. So I am using it. So what is it then, the matrix representation of the plus? Usually, when you read certain books, this simple, really childish derivation is not offered, as if you have two different languages and the ups and downs and matrices and all of a sudden coming out of that. No, here, this systematic construction gives you the derivation of this matrix representation. And similarly, what is the matrix representation associated with the minus basis vector? It is plus, minus, 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 right? Here is the ket in question, and here are the components of the bases, multiplying it. 0 and 1. Nice, because we have a good handle now. The basis vectors are already represented. What next? Well, the operator itself. What is the representation of the SC in this? That's a good point for a break, and we'll continue after that.